everyone. Great pleasure to have I lost track, I think is our 14th Marvel Distinguished Lecture. And today we have a special guest, is Professor Raffaele Resta from the University of Trieste. I'll give you later his short biography. But Raffaele has also been for a very long time engaged with many colleagues at PFL, so it's a familiar presence. Just in terms of bio, let me mention he got his laureate degree in physics at Scuola Normale Superiore in Pisa, and after that he immediately became what was called at the time a permanent researcher in the Department of Applied Math, well, not in the department, but in the field of applied mathematics. Sort of during those years, he also spent 2 years at SECAM in Paris, when SECAM was directed by Karl Moser, and also 2 years at EPFL in the late 70s, and that when many of these collaborations with the school started. When SISA, the International School for Advanced Study, was founded in Trieste, he was there as an associate professor. That I think was a very special time for the field of electronic structures, and there were Karen Farinello developing first principle molecular dynamics. Raffaele and Stefano Baroni were involved in the development of ideas related to dielectric response, and then leading to also linear response theory. Elio Tosatti was there, and many others. Raffaele became also a full professor in the Department of Physics in Trieste in the early 90s. Is well known for the development of what is called the modern theory of polarization in the mid-90s, early to mid-90s, that really linked this fundamental observable materials in solids to actually the very phase of wave function under parallel transport. And that was also extended to the case of magnetization with the modern theory of magnetization in 2005, developed by him and David Vanderbilt, and somehow simultaneously by Kian New in University of Austin, Texas. In addition to this, I always like to remind he did actually the first many-body perturbation theory calculation, what we call GW, in a molecule in 1977, so some really pioneering efforts, and also in general major efforts in understanding the dielectric property of solids. This is the long biography. The short biography is more fun. He told me that, I should say he's a senior postdoc in the lab now run by his son-in-law, and this is just because he actually formally retired from the Italian university system this year, and he actually is associated with a research center that happens just now to be run by his son-in-law. So with this, really great pleasure to have here and to do a broad lecture on geometrical and observable of the electronic ground state. Thanks a lot.
Thank you, Nicola. Yes, I would like to add something having to do with EPFL. I'm glad of being here, of course, for several reasons, but one is the following. As Nicola said, I've been tenured in Italy since the age of 24 until the age of 70. But despite that, a relatively large fraction of my professional life was spent here, always in kind of long visiting or short visiting, integrating over the years. That made a lot of time. And that was also the most exciting part of my professional life when the theory of polarization came out and the like. And also, I remember that when this site was just built, so the physics department of the EPFL was the very first to move from downtown Lausanne to this very new campus, and I helped with the moving. So I helped the moving in the very first rooms of this campus, with the people working at the lab at that time. Okay, now today I decided to speak of rather different things. I hope not to make confusion. That is, the point one is I'm speaking of geometry in some sense, in some flavor, and then point two for geometry in another flavor, and point three another more flavor. In point one, I will address all kind of material, that means material with correlation, material with disorder, that means Mott insulator, Anderson insulator, and even what I call band insulator, which are the most trivial. Band insulator is every undergraduate learns that in order to distinguish a metal from an insulator, it's enough to look at the band structure and check where the Fermi level lies. So if it is in a gap, it is an insulator, otherwise. So the very first is it's much more general than that, wants to address all insulators. The second point is that limits to band material. That means materials in a mean field sense where mean field applies, like Consham or Hartree-Fock. And so for those materials, I will not address whether they are insulator or metals, but simply I will show that there are several properties which are geometrical in nature, and I will focus on a few of them. And finally, in point 3, I will show that instead you can get rid of the K-space, you get rid of the reciprocal space, the block vector, and address the same physical properties in a completely different way. This is the most recent work we did. Finally, there are some simulations, and if I don't run over time, I also some addition, but this can be skipped, will probably be skipped. Now, the geometrical theory of the insulating state. So what is the most fundamental, the most elementary geometrical property you learn in calculus is a distance. So if you have two state vectors in any Hilbert space, you can define their distance in this way, that is minus the logarithm of the square modulus of the scalar product. So it is clear that this is gauge invariant. In this context, gauge means arbitrary phase factor. So if you can add and you can multiply those two with any additional arbitrary phase factor, this doesn't change. And the distance is so defined that it is 0 if the two quantum states coincide apart for a phase, and it is infinite if they are orthogonal. This is the definition. Alternatively, it is equivalent. This very, very simple geometrical property is the property which discriminates all kinds of insulators from metal. That is band insulators, Anderson insulator, Mott insulators, and more. And of course, I have to tell you what is psi1 and psi2 in this case. So it's clear they are many body wave functions. And this is the Hamiltonian. Suppose we have n electrons in a cubic box of volume L, is volume L to D the dimension, so L cube in 3 dimensions. Then the many-body Hamiltonian is the sum of the kinetic energies plus the potential. The potential includes the one-body potential, could be even disordered, and the two-body electron. All is in this V. This is a Schrödinger equation. This is a ground state. Now, the ground state obeys bond-form-Karman periodic boundary condition over a cubic box of side L over each electron coordinate. That means when you adopt a periodic boundary condition, the coordinates really are angles because you have a toroidal geometry. And then I need, besides the ground state psi0, I need to introduce an auxiliary state, which is psi0 tilde. It is the ground state multiplied by a product of plane waves, in a sense. This is a product of plane waves. And this also obeys the Bond-Karman periodic condition by construction. This is periodic, and this doesn't change the periodicity. And now, what distinguishes insulators from metals is this very simple quantity, the distance between psi0 tilde. In the large system limit at constant density, this goes to infinite in all kinds of metals, and this goes to 0 in all kinds of insulators. And that's what we came out with this idea in 1995 with Sandro Sorella. This was a kind of postulate, so we validated with a simulation on a Hubbard model, on a kind of Hubbard model, in order to have a correlated system, because of course we could prove analytically that this is true for a band insulator, a band metal. Then we had a Hubbard model. Equivalently, of course, the scalar product has a modulus which goes to 0 in all metals and has a modulus which goes to 1 in all insulators. And for a band metal, a special case, then there is a selection rule. You can prove analytically this scalar product is 0. So with our definition, distance is infinite even at finite size. You don't need the limit. If you have correlation, if you include correlation or disorder, then the selection rule breaks down, and you really have to do the thermodynamic limit. Now, to my view, the most successful application of this idea is a simulation run a few years ago by Sandro Sorella and his co-workers. And this is a very paradigmatic system, is a chain of hydrogen atoms. If you have a chain of hydrogen atoms at the independent particle level, you have at any interatomic distance, you have a metal, because you have half Philip bands at any lattice constant. But instead, Mott realized in 1949 that this cannot be true. At very large distance, you have an assembly of independent atoms. The wave function may change nature. In some sense, like in the hydrogen molecule. That means a very large distance, a good wave function is the hydrogen London, is not the molecular orbital wave function. And so the solid state analog, I would say, of the hydrogen London would give the right dissociation, but would give an insulator. And Sandro Sorel and co-workers, they have run a variational quantum Monte Carlo calculation up to 66 atoms with periodic boundary conditions, and they compute exactly this quantity as a function of the interatomic distance. And you see that for small interatomic distance, you have essentially 0, and you have 1, and the transition is somewhere here. It is steeper and steeper if you increase the size of the system, as you would expect. A better marker, for some reasons, we also know what happens in a non-interacting. Non-interacting, I told you already, it is 0, it is 0 everywhere, because in our definition of the scalar product, like Philip says 0, this is 0. They are orthogonal. Since we know how it converges with large L for some reason, so they plotted essentially this quantity, not only our distance, which is minus the logarithmic square modulus, but also minus n. If you do that, that is more clear. You see that beyond 3.5, beyond the interatomic distance 3.5, you have something which is essentially size insensitive. This is an insulator. So this is the Mott insulator. On the left, instead, you have something which becomes larger and larger and larger if the system increases. You can imagine that in the limit of an infinite chain, all of those points go up to infinite. So they could point out that the transition, according to their calculation, the Mott transition, paradigmatic Mott transition in a chain of hydrogen atoms happens at 3.5 Bohr. Next, I will switch completely gear, as I said, and I will concentrate only on band insulator, band metal, so no longer. I will define a different kind of distance, a distance in reciprocal space, a distance between not the distance between many body wave functions, but a distance between block orbitals. And to fix the notations, we have the Schrödinger equation in a periodic potential. V is a periodic potential, single particle Schrödinger equation. We have the block state, and the block state, as you all know, is a plane wave times a periodic function. We can also recast this as a Schrödinger equation for the U wave function, for the periodic function, and you have to change the Hamiltonian. The Hamiltonian becomes k-dependent formally in this way. If the potential is local, is this. If it is not local, there is also something here. And you notice you have a kind of vector potential or gauge transformation. So the k-dependence is in the form of a kind of peculiar vector potential. Now we switch to the distance between states at different k, between states at different k. And if you try to define the distance between block states, this is infinite always, because the block states at different k are orthogonal. But instead, what is relevant for geometry is the distance between the u, because this distance is finite. This distance is finite in general. And since it is finite, we can compute the infinitesimal distance, which is the basic quantity in all the differential geometry theories. You need the infinitesimal distance between k and k plus delta k, and G is the metric tensor, is a real symmetric tensor, is the metric tensor. And what comes out, if you do with this derivative, you find the expression of the quantum metric tensor is the real part of this minus this. This is also gauge-invariant. Something which I have to point out is that in general, when you write this, you are assuming that the u is a differentiable function of k. This is not what really happens in numerical work. If you are diagonalizing the Hamiltonian with the diagonalization matrix, in general, you get a random phase. So in general, they are not differentiable. So if you really want to, you have to take care to regularize the gauge or the like. So I would say we need the extra hypothesis that you are choosing a differentiable gauge, which is not the obvious thing, but in general. So if you have analytical formulas, you write in this way. When you discretize, you have to take care that when you diagonalize, you don't have, in general, a differentiable function by numerical diagonalization. So the quantum metric is one of the most fundamental, I would say, geometrical quantity, but there are other geometrical quantity which in physics are maybe more fundamental. And let me write the square modulus is just a matrix element times its complex conjugate. When I take the logarithm, I have the sum. And now you notice that each of these two terms is not gauge-invariant, because if I add an arbitrary k-dependent phase to the u, I have different terms. So this one is gauge-invariant, but this partition is not. We don't care much about that. We assume, again, a differentiable gauge. We suppose we have to make a definite choice of the gauge, And then, to expanding, you have a first-order term. And this first-order term is purely imaginary because of norm conservation. The real part of this is 0 because of norm conservation, which it is this matrix element plus the complex conjugate, and it is 0. So we multiply by I, and you get the famous Berry connection. So this is a real vector field. Which is gauge dependent, but is very useful in physics, as many of you already know, I guess, but I will say. If you take the curl of this, this is again gauge invariant. This is a gauge, this is gauge dependent, this is gauge invariant. In some sense, they have some analogy between the vector potential and the magnetic field, if you want. Vector potential is not gauge invariant. The curl of the vector potential is gauge invariant. But of course, we are not in coordinate space. We are in reciprocal space. So it's a kind of magnetic field in reciprocal space, is a kind of vector potential in reciprocal space. We can put together both. If you have many band insulator, we have n occupied bands, so you have a more realistic insulator with many bands. This is the Berry connection of the whole occupied manifold, so a geometrical property of the occupied manifold, where again we have a definite gauge choice. And then we can define a tensor which is more general. It embeds both the metric and the curvature, and this is we call F is the metric curvature tensor of the occupied manifold, written in this way. And the quantum metric is the real part of it, and the Berry curvature is the imaginary part. So they have some close relationship, real and imaginary part. And the curvature, we will see at the end of this talk, is also useful for metal. So we generalize, instead of summing of a number of occupied bands, we put the Fermi occupation function here. That means that this function, if you have chosen a continuous and differentiable gauge, you have a continuous function. This one is only a piecewise continuous, because there will be a jump at the Fermi surface. This is all what we need for the moment in the geometry. And then you may ask, what are the geometrical observables? So there is a list. Let me start with the maximally localized wave function, which is also familiar to many of you in this audience. Marzari and Vanderbilt, in this rather well-known paper, and quite much cited, they define the quadratic spread of the wave functions, and they find the gauge-invariant quadratic spread, which has this form. It is nothing else than the Brillouin zone integral of the Cartesian trace of the metric tensor, I say this is an observable. Why? Well, this was introduced as a formal quantity, and I guess was not realized by them that it is an observable. But why it is an observable? This is a very fundamental, I would say, very, very fundamental concept. We grew up with the idea that whenever you have an observable, you have an operator. So that is, you have an operator, and then the observable quantities are the eigenvalues of the operator, or the expectation values of the operator, of the like. And we had a way of thinking the reverse way. So if I have a measurable and observable quantity, I should find out an operator such that. But then in 1984 came out the very famous paper by Michael Berry, And I would say that if I want to summarize in a very few words the importance of that word, the word says in quantum mechanics, whenever you can write a gauge-invariant expression, this is something which is in principle is measurable. So the Berry phase is the simplest one. Berry phase, there is no operator. It's just a gauge-invariant phase of the wave function is measurable. So more generally, I would say the message, the outstanding message of this paper by Michael Berry is that in quantum mechanics, when you have something which is gauge-invariant, in some way you could find out that this quantity is measurable. And in fact, this is a measurable quantity. Everything is gauge-invariant, must be measurable. It's not a very natural and a very simple observable, so I will not tell you what it is, but however, sure enough, 3 years after the paper was found by Sousa, Wilkins, and Martin, which kind of observable it is. So ideally, you could perform some measurement and tell what is the experimental omega I on a given material. I will use this definition. A geometrical observable is any observable expressed as a reciprocal space integral for insulators, a Brillouin zone integral, or for metals Fermi volume integral, where the integral includes k derivatives of the U block orbitals. And these are the examples. Marzari-Vanderbilt quadratic spread is one. The quantum anomalous Hall conductivity in insulator is another one. The anomalous Hall conductivity in metals has some extrinsic part, but there is an extrinsic term which is also geometrical. Electric polarization, what was referred by Nicola, the orbital magnetization. There is the axion term in magnetic response, magnetoelectric response, and others. So this is a list of them. And for the time being, I will focus on two to give two examples and to discuss many features of those two, electric polarization and orbital magnetization, which are certainly those known to undergraduates, to elementary electrostatics, I would say electrodynamics, or simple what we call Physica 2, Physics 2 course. So second year of physics course focuses about electric polarization and orbital magnetization. We will give in a modern view, those two are geometrical observables. And here are the formula. If you go to textbook says that the orbital magnetization, the polarization is a dipole per unit volume, and the dipole is just the first moment of the charge distribution, which includes, of course, nuclei and electrons. You need charge neutrality. The magnetization is rather similar, is the magnetic dipole moment divided by the volume. In Gaussian units, I need a C here. And this is just the circulation of the microscopic current in the material. So these are the elementary textbooks. Of course, those definitions assume implicitly that you have a bounded sample. So you cannot use periodic boundary condition. And what is worse is that you have R, it is an unbounded operator. It is an unbounded operator. It's not a periodic operator. So those two expressions looks like dominated by boundary contribution. If you change the charge on the surface, then you get an extensive contribution to the dipole. That means a contribution to P. So they don't look like bulk property, although phenomenological they are. And furthermore, as a theoretician, we cannot evaluate them using periodic boundary conditions, because this does make sense when you have R. In fact, R is not an operator when you use periodic boundary condition. If you have a function which obeys periodic boundary condition, this defines a Hilbert space, multiplied by R, it's something which is out of Hilbert space, so it's not an operator. It's a forbidden operator with periodic boundary condition. That's the reason why the theory of polarization and of magnetization took so long. Polarization was understood in the 90s and magnetization in the 2000s. The formulas which came out at that time, here is the very famous formula by Vanderbilt and Keith-Smith, the Berry phase. What is here is famous Berry phase. The polarization, the electronic part of polarization is this expression plus the nuclei. And in 2005, 2006, we found out that magnetization has this form. Here I have a factor of 2 because I have a singlet ground state, doubly occupied block states. Instead, per magnetization, in general, the bands are split, so you do per spin channel. So this formula is not a factor of 2, is only for spin up or spin down, I would say. Now, when we discovered that, and you notice that they are geometric in the sense you have, it seems that similar problems have similar solution. That's what we emphasized at the time. We have a derivative of the u here. We have a derivative, a slightly more complicated expression, but still, let's say, two expressions of the same family, two resemblant. This also, notice, it is nothing else than the Brillouin zone integral of the Berry curvature. And this is, polarization is well defined only for insulators. It makes no sense to discuss the bulk polarization, static polarization of a metal. Instead, magnetization is defined also for metal. So we have here, you have a sum over the occupied states. So this could be, again, a piecewise continuous function, not a continuous function. Now, over the years, some years afterwards, slowly, the theory came in 2005, we realized instead they are not really similar. They are really similar, they look similar superficially, they are not. In fact, I would claim differences are more important than similarity. The polarization, you have a gauge-dependent integrand. The bulk polarization is defined as modulo a quantum, which I will explain what this means. And also, if you can tinker with the boundary, you can change the value of P. Instead, orbital magnetization, the integrand is gauge-invariant. The calculated magnetization, orbital magnetization has no modulo ambiguity, and you can do whatever you want. You can tinker with the boundary, but the value of M remains the same. So you see they are really opposite things. So these two observables, which are so similar, to our big surprise, those observables which are so similar in this definition, they are indeed extremely different from the viewpoint of electronic structure theorists. Let me explain what is the quantum. This is another important paper. This is not the famous paper. The paper of the very phase is King, Smith, and Vanderbilt a few months before this one. This one, the same authors in the reverse order, Vanderbilt, King, Smith, they came with the idea that bulk polarization can be defined, but at the price of accepting that it's not a vector, like in elementary textbook, is a lattice. And of course, when you use periodic boundary condition, the system by definition has no boundary. Of course, it's infinite in a sense. Your dielectric invades all space. You are using Fourier transform, Fourier series, whatever. That means you don't have boundary. It's an infinite system in a sense. And the value of the polarization remains ambiguous until the sample termination is specified. This is to explain what this means is particularly simple in one dimension. For a one dimension, the polarization is as the dimension of a pure charge. It is a dipole per unit length, so it is a charge dimension. It is defined as modulo E. The formula is P, the very phase formula tells is E over 2 pi times gamma. And gamma, as any phase, is defined as modulo 2 pi. That means that polarization is defined as modulo E. And if the system is centrosymmetric, then the lattice must be centrosymmetric. That means that there are two cases, either P equals 0 modulo E, or P equals E over 2 modulo E. Then, in order to illustrate, particularly to the chemistry community, to quantum chemistry community, we have run a simulation, a pedagogical simulation. This is polyacetylene. You see that this is a long chain. Here is only 5 monomers, but we went up to very long chains. We didn't use the Berry phase. We computed the dipole using the Gaussian code. There is no exotic Berry phase here. We computed the dipole with the Gaussian code. And we choose two realizations. With the bulk is centrosymmetric in both cases. The terminations are different, and both cases are not centrosymmetric. So you have to, this is a non-centrosymmetric molecule, this is a non-centrosymmetric molecule. They have the same bulk. The terminations are different, but both are non-centrosymmetric. So you expect that the dipole is non-zero in both. And sure enough, the Gaussian code tells us that the dipole is non-zero in both cases. But then we are interested in quantization comes out in the thermodynamic limit. What happens when the length goes to infinite? So we take many, many monomers, so what happens? And here is the result. We published this in Journal of Chemical Physics in 2007. You see that for few monomers, this is per monomer, for a few monomers, both have non-zero dipole, but then you go ahead, and you find that in one case we get 1. The lattice constant of this material that is 4.7. So this is per monomer. If you do per unit length, this is polarization is E here, and polarization is 0 here. So you have this is a nice realization of the fact that for a long monomer, the only possibility, no matter what you attach at the end, you can play with the end, you can vary ionicity almost continuously, but you have a jump because this is a topological aspect. In fact, the dipole of a chain of length L, if L is large enough, can be either 0 or plus or minus L times E. That's the same, that is like having a neutral rod with a charge E and minus E at the end. And so the end charge can be either 0 or E or minus E. And with hindsight, of course, something has already been discovered. Maybe some of you know that in 1979, this rather famous paper by Su, Schriffer, and Higger demonstrated that in polyacetylene, the soliton has a topological charge, in fact. It's a topological charge, and the mathematics is exactly the same. So it's a polarization, and the solitons are two aspects of this topological feature. Now let me go to, so we have found two different observables, which have two very different characters. And in fact, I will show you there are two families of them, not only two. The two observables, polarization and magnetization, are just two representatives of larger families. And the family is like this. The first family is the intensive observable is the integral of some function, and this function is gauge dependent. The bulk property is defined modulo quantum. If the sample is bounded, the value depends on termination, although should be one of the quantized values. Polarization is this, but there is and mathematicians would call the integral of the Berry curvature would call it a Chern-Simons 1-4. And then mathematicians invented all odd terms, 1 form, 3 form, 5 form, 7 form. We stop at 3. But the Chern-Simons 3 form, which has a rather complicated expression in terms of a K integrand, has to do with a response of magnetoelectric materials. And so this is a very elegant work which has been done by Joel Moore, and again David Vanderbilt and other authors. And so these are really two observables in the same family. They have the same feature. This is much more complicated, but in the same family. The other family, instead, there is magnetization, which I already discussed. And you have an integral you have an integral of the Brillouin zone, but even if you have a metal even on the Fermi volume of a function, which is gauge independent, you don't have any quantum ambiguity. No matter how you cut the finite sample, you get the same result. And there are those. The quadratic spread, which is defined only for insulator, the omega I is here. I will not speak of the Drude weight, but instead those two, I already discussed orbital magnetization. There is a very close relative. It is the anomalous Hall conductivity. So they are close. Both require absence of time reversal symmetry, and both are well defined in either insulators or metals. The only difference is that the integrand here is a continuous function in insulator, is only piecewise continuous in metals. This is the intrinsic term in the anomalous Hall conductivity, so the antisymmetric part of the conductivity tensor at omega equals 0, DC, is just the integral of the Brillouin zone, on the Brillouin zone of the Berry curvature, which is a gauge-invariant quantity, is written this way. This is necessary. Now, there are extrinsic. What about extrinsic terms? Extrinsic terms necessarily are present in a metal because otherwise the longitudinal conductivity would be infinite. You have a finite conductivity only if you have extrinsic term, because if you have a band metal, you apply an electric field, the electrons undergo free acceleration. So if you want a steady state current, if you want a Ohm law, you need some extrinsic term, and the extrinsic term also affects the transverse conductivity. But there is one part which is not extrinsic, it's just geometrical, and it is this. Now, instead, why it is absent in insulator? Because in insulators, the longitudinal conductivity is 0. And this quantity is topological. And as a basic tenet of topology, insofar as the system remains insulating, you can add impurity as you want, the conductivity cannot change. The formula for the orbital magnetization is the one I've already shown. So you see there is, again, some similarity between this and this. It is the imaginary antisymmetric part. It is the imaginary antisymmetric part of two things which are, in some sense, close relatives. Now, we came with the most recent work we did. Periodic boundary condition and K-vectors are a very useful creation of our mind, but they don't exist in nature. The material doesn't know that the K-vector exists. And so a genuine Bull property should be measurable inside a bounded sample, like bounded crystallite, for instance. In a non-crystalline sample, in heterojunction, you could find magnetization in some value on the left of the junction, a different value on the right. I cannot do in K-space, because K-space implies periodicity. Even if I do a supercell, I would get a kind of mean value. I would not get, wanted to say. So what can we do in that case? And this is what I will try. We provided the geometrical parquet directly in K-space for both those properties. That means anomalous Hall conductivity and orbital magnetization. The key ingredient is the ground state projector, or the one-body density matrix, which is something like that. And this is, if you have a non-interacting system, now I'm addressing a bounded system with square-integrable wave function, so a finite crystallite, a bounded crystallite. This is the ground state. If you know this, you know any ground state observable, you know even the wave function. P is enough to determine anything. You can determine wave function, energy, all physical properties. Of course, if you have crystallite, you need P in all space, including close to the boundary. Now, what we have done, I will not give you the algebra and how we arrived at this, but we give only the result. We have defined a tensor field in real space, in coordinate space, or let's say in shading representation, with this operator and this operator, F and M. And notice that in the bulk of a crystallite, those two tensor fields are lattice periodical. Why that? Because P is for sure lattice periodical. I have a crystallite, I look what happens in the middle, in the central cell, in a sense, it is periodical. Now, R is not periodical, but the commutator is. So in a sense, P tames the nasty R operator. So R is not an operator, but R commutator with P is. So this is the key translating from K space to R space. I will not give you the algebra. And I will show our formula. Our formula is that the anomalous Hall conductivity can be evaluated as the trace per cell of this tensor field, and magnetization also as the trace per unit volume. But per unit volume means that I have a bounded sample. I take, for instance, a cell in the middle, and I calculate this. And this we demonstrated as usual. In order to see that this works, we made computer simulations. Our favorite tool are computer simulations. And the workhorse for those simulations is Haldanum. Haldanum is like massive graphene or boron nitride, if you want. But you need to break time reversal. So you have a tight binding model with first neighbor hopping and staggered on site. Up to this point is just a regular model for regular boron nitride, and you break time reversal with the second neighbor hopping like this, in his, this is a very famous paper by Duncan Haldane. In his Nobel lecture, which is online, he said that in order to find this, he had to add some magnetism. Some magnetism is this. You can imagine the system is periodical, so you have just plain vanilla block states. So the band structure has nothing exotic. Like instead, if you have a macroscopic magnetic field, you have Landau levels, you have Hofstadter butterfly, you have many exotic things. Here, if you look at the bands, you have just regular block states and the like. It's like having a magnetic field which is staggered, which is, say, up in one half of the cell, down, because the flux per cell is zero. The key point which allows you to have block states is that you want the magnetic flux per cell to be zero. If you have in case instead you have a macroscopic B field, magnetic field, the Hamiltonian cannot be lattice periodic in any gauge. Instead this Hamiltonian is lattice periodic. So if you do a half filling, it is a two-band system. Of course, it is a two-band system. If you put the Fermi level in the middle of the gap, it is insulating and can be a topological insulator. Depending on the parameter, the great discovery of Duncan Haldane is that it can be topological. Depending on the parameter, it can be trivial or at any filling different from one half, it is metallic. We use it both the insulating and the metallic model. As I said before, there are extrinsic mechanisms, side jump and skew scattering, but it was clear that it came out relatively late. Only in 2004, 2005, people realized that there is an intrinsic contribution, which is nothing else than the non-quantized version of the quantum anomalous effect. So the non-quantized version essentially of the Haldane discovery, if you want. And we have proved that it is locally in R space, both in insulators and in insulators, I will not show here, but in metals. This is the simulation made by Antimo Marrazzo, who is here. This is a typical flake of Haldanum. We have a bounded flake of Haldanum. Up to 8,000 sites. I will also show next what happens on this line. So this gray line will show what happens next. And we computed the trace per unit volume either on a cell with two sides or in this part or in the whole sample. So there are three ways of computing the trace per unit volume. Trace per unit volume can be trace over all of the sample divided by the surface by the area of all of the sample. Can be the trace over this rectangle divided by the area of the rectangle. It could be on two sides a single cell divided by the area of the basic cell. Now, this is the anomalous effect, which we published about 1 year ago. The solid line is the usual K space, the Fermi volume integral, and the symbols is our R space geometrical marker. And you have different ways of taking the trace per cell. Now, we choose two different set of parameters. This one is trivial half filling. What does it mean? This is the bottom of the lowest band. It is a two-band model. This is the bottom of the band. We go up with the Fermi level. Then the anomalous conductivity goes up, then goes down, and it's zero. Here we are insulating regime. When the Fermi level mu is in the gap, we have zero, and the conductivity is zero. And then start again, and if we fill both of the bands, it will be zero again. This one has a different set of parameters. You start for the band, go up. When you are in the insulating regime, which is here, mu in the gap, then the transverse conductivity is not zero, but it is quantized. It is quantized, it is 1 in these units, because this is topological, it's the famous Cher number. So this is a Cher number. We wanted to show that works in heterogeneous material, so we have chosen an heterojunction. That means we suppose our flake is cut in two. There are two different metals on the left and on the right, and we show what happens on this line. We show what happens on this line, the function to be integrated on this line. And this is here. You see that if you take the average over two sides, so the cell average, that means cell over two average, it is a constant, and here is a different constant. You can easily recognize the two different metals with two different values of the anomalous Hall conductivity. And the solid lines are computed in reciprocal space. So suppose we have just a simple crystal of one kind of metal, and we compute the anomalous Hall conductivity as everybody does. You find this line, and you find this line. So this shows that our local approach works perfectly on this test model. One important point is the convergence. The textbook formula is the one I've shown earlier. The reciprocal space formula is this one. Our novel formula is this one. At convergence, all three gave the same result. But now, how do they converge? How do they converge? And here is the very interesting point, that if I use the textbook one, the convergence is like, in both metal and insulator, the convergence is this one, is just like the inverse linear dimension of my system. Both metal and insulator are nothing to do, both formulas, my formula, because they are identical. The point is that if instead of taking the trace over the whole sample, I take the trace over a small part, say a cell in the middle of our sample, then the convergence in insulator is exponential. And in a metal, it is power law, but with a law much better than this one. That means that if I want to define what magnetization is in the large L limit, I don't have to use this. I have to use this with a small cell in the middle. And with this, I'm perfectly on time, I guess. And the conclusion is that a simple geometrical, the first part of this talk is that a simple geometrical quantity, that is a quantum distance, discriminates between any kind of insulator, any kind of metal. Then I have specialized it only to band insulator, band metals, and I convinced you that there are two very quite different families of geometrical observables. They come in two different classes. And the third part, I've shown that geometrical or topological features, geometrical and topological in a sense are, with our tools, are the same. They are described as the same tools. In some cases, they are quantized, in some cases are not. So geometrical quantity, when it's quantized, it becomes topological. But we use the same tools. Of course, for mathematicians, it is an heresy to say that topology and geometry is the same. They are completely different things. But in our business, let's say, geometry and topology requires the same kind of tools. I've shown a simulation of Haldanum flakes, bounded, locality of anomalous conductivity, locality of orbital spontaneous magnetization. There are also published results not presented here, a simulation of non-crystalline flakes, so in a disordered flake. There is a locality of quantized anomalous Hall conductivity into the insulators. And there is also a locality of induced orbital magnetization with B in non-zero. You cannot have a B non-zero in a periodic system. As I told you, you have all kind of exotic phenomena. But if you have a finite crystallite, a finite flake, you can switch on any B you want. We did that. And we are working at the quadratic spread, and making local the quadratic spread and the theory of the insulating state, and also the locality of the Drude weight. The most recent work has been done in collaboration with my former students, Antimo Marazzo, who is here, and Raffaele Bianco, who now is in California. And also, these are the published papers, and also have a paper of mine which was rejected by physical letters. I decided not to publish. So it is. I have this privilege, being retired, and being a single author. I prefer not to publish, and it is on the archive. And with this, I thank you for your attention.
This bird's eye view on geometry and electronic structure. We have time for questions. Maybe I'll start with one. So sometimes we deal with many body wave functions, sometimes we deal with slated determinants. And to me it was not always clear if there is always a correlated electron and a single particle electron picture, the way I think at it, say in the case of the single point very phase formula for the polarization, or if some of these discussion only refers to say single particle picture as we are used to.
Yeah, I've avoided in this talk to describe, besides the insulating state, that means besides discriminating within a material is metallic or insulator, I didn't tell anything else about correlated system, but instead, but some of the observables in the list, that is, some of the observables in the list also have a definition for correlated wave function, which I have not shown here, which obviously goes over the band structure case if they are non-correlated. So let's go to the list. No, it's better to remain here. So we know how to compute and how to define and compute polarization also in the correlated case. So for a many-body wave function, and the many-body polarization goes over into the block polarization in the uncorrelated. Nobody knows how to do that, for the axion is already difficult enough. The axion has difficulty even in discretizing, because if you do it numerically, if you diagonalize, then you cannot. So the discretization is very difficult. People are working on discretization. For sure, nobody addressed the axion term in a correlated material. Next, instead, we know what is the analog of the quadratic spread for a Mott insulator. Essentially, what I've shown in the simulation by Sorel and co-workers was nothing else than the omega I for a Mott insulator. So we know how to extend the omega I to a Mott insulator. We know how to extend the anomalous Hall conductivity, at least for a correlated insulator, not for a correlated metal, but for a correlated insulator, yes. So the many-body Chern number has a definition, we know. Unfortunately, we don't have anything beyond independent particle for the orbital magnetization. In the Drude weight, instead, there is a very famous definition by Walter Kohn, 1964, which is precisely for the correlated case. So I would say this and this, it's pretty clear what you have to do when you have correlation and interacting electrons. This one, only in the case of insulators. This one, no, we have not yet solved the problem. I don't know whether this was your question, essentially.
I like it when something doesn't fit, because it means that there must be something that we haven't discovered yet somehow. And say, take the case.
I can tell you something which could be cryptic, but the difficulty is that the magnetization is the expectation value of essentially Ri dot Vi. Instead, doing that naively, you would get the expectation value of sum over ij Ri vector Vj. This is easy, but this is not magnetization. This is the point. This is the point. Yeah.
But well, I don't know.
Yeah.
I mean, so this is one sort of great spot. The other is, and maybe this is my naivete in quantum mechanics, I mean, and maybe because I've always been taught about thinking that operators, so can one prove that there are no operators that give you something like a very phase that is, that one cannot define?
I would say for the polarization, for sure. Instead, the operator of this family, we have shown that, in fact, they can be converted into an operator definition, because what we have finally is the expectation value of a rather complicated operator. Yeah. So that's true. If you want to insist that you have a property which comes from a gauge-invariant property of the wave function without any operator, then this is the polarization and also the axion term. Here there is nothing else. And
but it's just because we haven't found anything.
No, I think it is impossible to find.
Okay.
It's impossible to find because this has to do with the fact that there is this quantum, that is, you don't know what the value is until you specify the termination. So they go 1 to 1. So my view is that these two, really, it is impossible to find any operator. Really, these are a gauge-invariant property of the ground state, in a sense. But instead here already the difference, if you want to be more precise, the difference is here you don't have any Hamiltonian, here you have an Hamiltonian, you see. Yeah. Yeah.
Yes.
You showed this list of geometrical observables, and I was wondering if there is the complete list, or is there a systematic way to collect or like find these geometrical observables that you have this definition about?
To find them, any more geometrical observables beside this, you mean?
Yes.
No, there is no systematic. I would say even, let's say even the axion, I would say, was a big surprise and success. So a few years ago, somebody came out with the idea that in the magnetoelectric response there are several terms, but at the end there is one term which is a geometrical property of the ground state. So this is the most systematic which I can arrive is this. This clearly I can show why there are these four, but yeah.
Maybe a last question that goes back to my sort of love of density functional theory.
Yeah.
And there is this, famous GGG theorem from
Yeah.
the mid-90s that you probably remember.
Of
it's
course.
shown
Of
that
course.
in a periodic system, what is usually called the density functional theory of the densities are the density functional theory of the polarization.
Yeah.
And it's always been mysterious to me why we were able actually to describe a polarization well without having a polarization in itself in exchange for a function.
You know that Hardy Gross is retiring. We wrote a paper for his first script, and my paper is about that. So I will give you. But let me explain in a few words the following. If you have a bounded crystallite, by definition, the exact density functional theory gives you the exact n of r. And so the exact n of r, of course, gives you the exact dipole and the exact polarization. By definition, if you use a bounded system. Now, if you adopt periodic boundary conditions instead, the density has nothing to do with polarization. It's not a property of the density. It's completely different. It's mostly a property of the current in the sense that the difference in the idea beyond the archetype of the modern theory, that is the way I presented after which David and Dominic found the very phase, the idea was that delta p is equal to the integral from 0 to delta t of j of t in dt. Yeah. And now, of course, this can be done in periodic boundary condition because j is well defined. So this was our idea. Incidentally, we tried to compute this. Is also some history. We tried to compute this. When I presented this as a conference, then we were working with Michel Pasternak calculating this. Since Michel Pasternak uses LAPW code, which is strongly undercomplete, we had difficulty in computing this. And then a couple of months afterwards, I went to another conference, the electronic structure, I guess in Philadelphia. There was David and Dominic Smith. They had a poster. They converted this into the very phase. But if you look at this, it is clear that density functional cannot give you the J. Cannot give you the J. So the relationship in a bounded crystallite, if you imagine that I have a slab, and I switch on a field and I polarize. After the polarization, we have a charge here, and I can compute polarization using the charge, including the surface. Now, if I sit in the middle and I don't access the boundary, can I compute the polarization? The answer is yes. It's enough to compute during the switching off to compute the current which flows. This gives you polarization. But the point is that density functional theory doesn't have anything close to a continuity equation. So you don't have continuity equation. In density function of C is static. There is no time dependent, not even adiabatic time dependence, except in the ALDA. In the adiabatic local density approximation is okay. But the exact density functional, you cannot rely on any continuity equation. And this is essentially the reason why when we wrote the very first papers about polarization, we had the idea, very naive idea, that since supposing somebody gives you the exact constant potential, you compute the exact polarization. But instead, with hindsight, this is very naive because polarization is not a function of the density. So
in that sense, it's surprising that you actually get meaningful results.
No, the point, the way I present this, even in the paper I give you, is that this is an intrinsic error as a matter of principle. And then there is a second error. You will never know the exact density function. So which part of the error is due to the actual density function, which part of the error is due to this intrinsic is not known. It is true that we get 5 to 10% in polarization of ferroelectric materials and the like. However, it is good to know that if you take a polymer, and we take a finite polymer that is bounded, so for which the density function material is valid, so you don't have this problem. Well, the polarizability by the common functional is off by a factor of 2. So it's very difficult, at least for quasi one-dimensional system, it's very difficult to get polarizability with all of the usual functional. In three-dimensional, for some reason, instead for a three-dimensional bulk system, works well. We don't know why. So our very first calculation, I think the very first calculation historically was the electric contact of silicon with I and Stefano Baroni in 86, and we have got maybe 10 to 12, 10 or 15% higher than experiment. That was big. So the local density gives already 10.
Okay, I think if there are no more questions, we can thank Raffaele again.